Good afternoon, everyone. My name is Hyunsung from Yonsei University in South Korea. The research topic is design assistant for excavation support system in a large construction project. Some of you may be unfamiliar with an excavation support system. An excavation support system is excavation support system that protects the construction site and prevents the inflow of soil and underground water. So it typically consists of three main components: retaining wall, water barriers, and lateral supports. From this point on, I will refer to excavation support system as an ESS, an abbreviation. In this presentation, I'd like to introduce a method that supports the design process of an ESS. In previous studies, only one retaining wall per construction site is recommended. As a result, selecting a specific ESS for each excavation site, as well as detailed design parameters such as wall thickness or pile diameters, still required additional input from engineers. In this study, we propose a method that can recommend the suitable ESS components and its design parameters for each excavation site, not for entire construction site. Furthermore, it allows for the generation of a 3D draft model of the ESS design. So now, the research objective is as follows: to develop an ESS design assistant which is capable of recommending appropriate ESS components and their design parameters for each excavation site. First, we collected ESS cases from real ESS projects, then training machine learning models by using two recommendation process. The first one is independent process, and the other one is dependent process. During the training, we tuned hyperparameters to gain the best performance. Finally, we analyzed the results by using Wilcoxon signed rank test in order to validate the examined and meaningful difference between the recommendation processes. Pictures in these slides show the example of ESS data. We collected 13 selection factors for ESS recommendation, which can be gained from public data. Building information is provided as a shapefile from GIS dataset, and the ground information is provided in tabular format. Totally, over 1,800 cases were collected from 124 excavation projects. We experimented with two machine learning approaches to recommend both the ESS components and design parameters. One is the independent recommendation, and the other is the dependent recommendation. In the independent recommendation process, once the input selection factors are provided, the ESS components and design parameters are recommended individually. And on the other hand, the dependent recommendation process follows a process more similar to the actual design process. One suitable method for the retaining wall, water barrier, and lateral supports are selected. The corresponding design parameters are then recommended sequentially in relation to those components' choices. In order to evaluate the two recommendation processes, we experimented with a range of machine learning algorithms, including decision trees and support vector machine and XGBoost and so on, and enhance their performance through hyperparameter tuning, including by evaluating learning rate and the depth of trees and the number of estimators and etc. Since the retaining wall is the first component to be recommended, there is no results available for the dependent recommendation in this case. However, when applying the dependent recommendation method to the other components, The water barrier achieved a maximum performance of 0.981, and the lateral support achieved 0.831 of weighted F1 score. Overall, the dependent recommendation process consistently outperformed the independent recommendation process across all experiments except one case. We observed a performance improvement of approximately 2 to 10% when using the dependent process. Furthermore, the design parameters associated with ESS components such as wall thickness and pile diameters and center-to-center spacing of pile all demonstrated high recommendation performance with weighted score above 0.92. To determine whether the performance difference between the two recommendation process was statistically significant, we conducted a Wilcoxon rank test. The results show that the p-values of both the ESS components and design parameters were below 0.05, which indicates a statistically significant difference. Therefore, we accepted the alternative hypothesis that the recommendation process had a significant effect on the recommendation performance. This is a demonstration video showing the recommendation model is integrated into an ESS design tool to generate ESS design alternatives. The user begins by entering the project address and placing the excavation footprint on the site. If selection factors such as ground information or building information exist, then they are assigned to each excavation site automatically. Once the set of selection factor is provided, the pre-trained model recommends the appropriate ESS components and design parameters. And using the recommendation results, a draft model of the excavation support system is then automatically generated through parametric modeling. If any modifications are needed, the user can click on each component to adjust its dimensions. For the conclusion, this study goes beyond simply recommending ESS components for each excavation site. It also provides design parameter recommendations and even generates a draft beam model. The selection factors used in the model are primarily based on publicly accessible data, and publicly accessible information, making the approach practical and scalable. In addition, the dependent recommendation process demonstrated higher performance compared to the independent approach, highlighting its effectiveness in real-world design scenarios. However, there are also some limitations. First, the design assistant is currently based on commonly used construction methods. Therefore, for specialized or less common techniques, additional data collections and model training will be required. Second, although the system recommends design parameters, there are suggestions only. So for actual implementation, the recommendations must be reviewed and interpreted by engineering experts. For future work, we are exploring methods for rule-based compliance checking of the generated 3D models. We are also working on expanding the range of ESS components supported by the system in order to improve the completeness and applicability of the generated designs. So these are references of my research. And thank you for listening.